In this video, I want to define the idea of the dot product. We're going to start with two vectors u and v in Rn. Well, the dot product is defined as u transpose v. And this is denoted by u dot v, hence the name dot product. So essentially, I'm just multiplying u transpose times v. So whenever I transpose a vector, instead of a column, it's now a row. So I have something like u1, u2, all the way up to un, times my vector v, which says v1, v2, all the way down to vn. So when I multiply these, I multiply row by columns and add. So I would multiply u1 times v1 plus u2 times v2. Continue this process at the very end, un times vn. So we can find the dot product by multiplying things in corresponding positions and adding them up. Let's look at an example. Here I have two vectors u and v, and I want to find u dot v. So we multiply things in corresponding positions. The first entries are 1 and -1. Then we add the second ones, 1 times 0, plus -2 times 5, plus 5 times 1. This will be -1 plus 0 minus 10 plus 5, or -6. So the dot product here is -6. A few quick properties about the dot product. First, u dot v is equal to v dot u. Switching the order here doesn't matter. It is commutative. The second one, we do have a distributive property. U dot v plus w is equal to u dot v plus u dot w. So the distributive property here does hold. The third one, c times u dot v is the same thing as c times u dot v, which is the same thing as u dot cv. So I can move scalars in and out. I can multiply the scalar by any one of the vectors and then take the dot product, or I can take the dot product first and then multiply by the vector. And the fourth one, v dot v is always greater than or equal to 0, where it's equal to 0, so v dot v is equal to 0 if and only if v is equal to 0. So I'm going to talk through the proof of this one very quickly. So v dot v, we multiply things in corresponding positions and add. So we have v1 squared plus v2 squared all the way up to vn squared. So we can see we square a bunch of things, so these are always positive, and then add them up. And the sum of a bunch of positive numbers is always positive. In addition, the only way for this to be equal to 0 is if each one of these terms are equal to 0. In other words, v is equal to 0.